In this lesson, we're going to learn what a calorimeter is and how this device, a calorimeter, can be used to measure the heat exchange between two objects. Now we're going to focus today on how do we use a calorimeter to measure the heat capacity of a metal, but in the future know that we're going to use the same calorimeter to measure the heat exchanged in a reaction as well. And there's a specific strategy that I'm going to suggest we use. It's called the system surrounding strategy to help us solve these kinds of problems. I will also say, you know how I mentioned in gas laws that the one type of problem that people sometimes struggle to remember at the end of the year was how to measure the molar mass of a compound with a gas? Well, it turns out how to do calorimetry problems is the one thing from thermo people don't remember very well at the end of the year. They remember how to use Hess's law, they remember how to calculate the free energy, but this act of how we physically measure heat exchange in lab with calorimeters can be something that's difficult to remember. So you want to have nice, neat notes on this. Okay, so I'm going to get rid of me because we got a lot of problem solving to do here, but we're assuming that we don't know the heat capacity of the metal. And that's something we want to measure. Now, this is a little bit hypothetical because you might be thinking, well, there aren't any new metals in the world. Don't we already know all their heat capacities? And the answer is yes. So one thing we're doing is seeing how they determined this using a calorimeter. But the other thing we're doing is, of course, new metals are created all the time as you make alloys, you make mixtures, and of course, those have different specific heats. So we're going to use a calorimeter to figure this out. And here are a couple of examples of calorimeters. On the left, we have something called a bomb calorimeter. And on the right, we have a styrofoam cup calorimeter. Any guess which one of these two we actually will be using in lab? Now, if you said neither because you think we're not going to be doing labs, that's a little hurtful. But yes, we don't have a bomb calorimeter. We only have styrofoam cups, but they work great. You'd be surprised how good the results turn out. Now, of course, at home, I didn't do, you'll see, we're about to do a lab, and I didn't even use styrofoam cups. But of course, the goal is to keep them pretty well insulated so that, you know, heat doesn't leak out. They always have a thermometer in them because, of course, you need to measure temperature. But a bomb calorimeter is useful whenever you're doing a reaction that's not aqueous, right? If you're doing a reaction and it's aqueous, this works great. But a bomb calorimeter will let you isolate the stuff inside a small container. And the water you need for every calorimeter is sort of on the outside. So now we can do non-aqueous reactions like, say, combustion reactions, or we can do what the food industry does, is they use a calorimeter to measure the amount of heat that would be absorbed by your body if you ate some food. So whenever you see the sort of calorie content of foods, they've used a bomb calorimeter to figure this out because more or less they combust these things, light them on fire, and you can't do that in water. So in that sort of circumstance, a bomb calorimeter is really important. But any calorimeter measures the heat exchanged by objects, and this one works great. By the way, we do have the budget to nest 2 of them together for extra insulation. So, yeah. Okay, so how are we going to get this to work? Well, if we're going to use a calorimeter to measure the specific heat of a metal, essentially what we're going to do is we're going to get this metal to be scalding hot in any way you can. Like, for instance, in our lab, we have an oven, and very often we put it in the oven, and then we plunk it in some cold water and see how much it warms the water up. Right? That's one way to do it. Sometimes they take the block of metal into a separate beaker of boiling water and they boil it, and then they throw it into the water. You just have to have some way of getting it warm, and you'll see how I did this at home in just a minute. But essentially the idea here is the heat that is leaving the block, which tells you what's Q for the block. Is it positive or negative? Well, it's negative. The heat leaving the block will be absorbed by the water, and that's positive from the water's perspective. But the thing is, those amounts will be the same, right? So if this block gives off 500 joules of energy, the water will absorb 500 joules of energy. Well, you can imagine if we have our thermometer in here and we're measuring the temperature increase of the water, that will let us calculate how much energy is absorbed by the water, and we can assume that that was how much energy was given off by the block. So that's the idea behind calorimetry, is it's an exchange of heat. Now, I'm going to recommend that we divide up our work into system and surroundings. Any guess what the system is? Well, the system is going to be the block, because that's what we're trying to learn the specific heat of. We want to know the specific heat of, I don't know what it will be, aluminum, copper, something like that. So it's going to be our part of interest. The surroundings will be the water. And we're assuming it's just the water because we're making an assumption that all of the heat that comes out into the water is absorbed by the water, and the change in temperature is only because of that. Now, you know, if we leak a little bit of heat out of here, then that's gonna be a problem for us. We're not going to see as big of a change in temperature, and that might be a good error question, right? But we're going to assume that these nice doubly insulated cups do a great job of keeping all of the heat inside. Okay, so here's our strategies. Our strategy is going to be, if we can measure the heat gained by the water, we will know the amount of heat lost by the block. And if we know the amount of heat lost by the block, we will be able to calculate the specific heat of that block. So the way I always recommend that you do calorimetry problems is you divide your page up, divide it in half, and I want you to get an example like this in your notes. The metal that you're trying to figure out the specific heat of, if it's zinc or something like that, that's your system. Actually, I don't really want to write that there. You'll see in a second. And this is the surroundings. We need to measure everything in Q equals mc delta T about both of these. We need to know the mass of the water, the specific heat of the water, and the change in temperature of the water. That's going to go up. For the metal that we're going to look at, we need to know its change in temperature. Now, it will be hot and it will be colder at the end, but we can still measure its change in temperature. We need to know the mass of that metal, and if we know all of those things, we can solve for the specific heat of that substance. So always divide your paper into system and surroundings, and I will tell you that we always do our work on the water side first. We use it to calculate Q. Once we know Q, we will know Q over here. But remember, this will be positive and that will be negative. We'll have to change the sign. Once we know Q and M and delta T, we can solve for C in this second part. Okay, so let's try it out. So what we're going to do is we're going to play this little measurement here that I did at home, and we're going to see what measurements we can record. So it looks to me like I'm about to throw the metal on there. By the way, I don't know if that's zinc or not. 70.77. We'll say 70.77. Now you're about to do one of these on your own, so here's how I heated up the metal. Is I just threw it in the oven, turned the oven on. Now I needed a temperature for that oven, so you'll see I put a little temperature probe in there. And we're paying attention to the one on the left over here, not the one on the right, because that's just a set temp. So it says 211, 211, maybe 212, we'll see. 213. So the hot metal will be at 215. We'll see, but we'll keep an eye on that. So I'll say the initial temperature of the metal. Oh, there we go, 228. The initial temperature of the metal is 228. All right. So I'm actually going to do this measurement, not in a styrofoam cup, but just in this beaker. I know it's real sloppy, but that's okay. We're gonna get some water, and of course, you remember I need to know the mass of the water. So let's see what it says here. I might need to freeze it if it's really quick. Oh, 45, 46. I'm gonna say 46.6. 46.6. That's milliliters, but of course, if we assume it's 1 gram per milliliter, we can go with that. All right, so I dump it in the beaker, and now we're going to take that scalding hot metal and dump it in there. The initial temperature of the water is 19.6. All right, we throw it in there. Now watch how fast this happens. We're looking for the highest temperature it reaches. 27.6, 28, 29, 33. We're looking for the highest temperature, 35.7, 36.3, 37.0. 37.7, 37.8, 37.9, 38, got up to 38. Let's see, 38.2, 38.3. Maybe that's it, 38.3. All right, looks like it stopped, and I bet it'll start coming back down here, because you know this thing will start releasing heat to the air around it. So I think I'm going to say 38.3. So the final temperature of the water is 38.3. Yep, look at it. It's starting to come back down. All right, now before we go any further, what is the final temperature of the metal? Well, it's sitting in there as well. So its final temperature is the same. It's 38.3 degrees Celsius. That's a really important thing you need to get in your notes, which is the final temperature of both is the same. And what you're looking for is the highest temperature that the water gets to. Super important. Okay? All right, now we have all the information we need. Now, if we're going to calculate the answer to what is the specific heat of zinc, remember that's what we're after here. Remember, we always start our calculations on the water side because we know most of the information. We know that water is 4.184 joules per gram degrees Celsius. We know the change in temperature is going to be these two, so I'll subtract that. All right, so I got 18.7 degrees Celsius when I subtracted those two. And now I can plug in Q equals MC delta T, and I can find out that this water absorbed positive 3,646 joules. Okay, that's a great start, because now if I'm going to figure out the heat capacity of zinc, I need to know the heat, which of course the heat is now going to be, well, let's do it down here. Q equals MC delta T. The heat is going to be negative 3,646 joules. We know the mass was 70.77 grams. We are trying to find the heat capacity of the zinc. And we know that the change in temperature was final minus initial, so 38.3 degrees Celsius minus 228. And then I can solve for my specific heat of my zinc. And when I do that, I get 0.272 joules per gram degree Celsius. You know, I'm not sure that this is going to be the best result. Maybe on the next page we'll see it. But in any case, because, you know, we didn't have a styrofoam cup, I suspect some heat leaked out a little bit. But it's a reasonable specific heat for a metal. So that's how you do it. In summary, divide up things into system and surrounding. Oop. Oh, we can see it. 0.389. What did we get? Oh, yeah, we were a little bit low. But in summary, divide up everything into system and surroundings. And then remember, which side do we solve first? Definitely the surroundings. Go down the surroundings first, do Q equals MC delta T. Once you get Q and you get a value, if that comes out to be positive 100 joules, and you guess what Q will be over here? Negative 100 joules. And then we'll know the mass and the change in temperature for that substance, and we can solve for the specific heat of that metal. And one last thing, to make sure your signs are correct, remember two things. We got to do final minus initial, always, because that's where the sign's going to come from. And then specific heats are always positive. They are always positive, right? Look at them all. They're positive. So you'll know if you messed up the sign in any way. All right, let's try another one. Let's do this one. So divide up your paper into system and surroundings, and I want to play this video. I want you to record the data. We're doing a lab here, so I want you to record the data, and then I want you to calculate what is the specific heat of this metal. No cheating, by the way, no looking it up, because you might think that looks like the copper we used in a previous video. But maybe it's a copper alloy. We don't know. We'll see. All right, here goes the video. Oh, one last tip. Don't forget that on the thermometer, it's the left one that we care about. I think one of the reasons why we might not get the most accurate results is you could see I wanted to stir it. I usually put a little hole in the top, but I forgot to put the hole in the top so I couldn't stir it. So maybe that's one of the reasons we may not get exactly on the money results. That might be it. Oh, it went up 1/10 there. All right, so do your calculations. I think that's probably it. Do your calculations and then type in your answer. Okay, so here's what I did. These are the measurements I took. So starting on this side, let's see. I thought 41, 42, 43, 44, 44 point something. Let's see what I chose here. I got 44.8. Seems reasonable. So you may be off a little bit, but that's what sig figs are about, right? You may disagree with me. Specific heat of water, that's easy. That's always 4.184. Change in temperature of the water, well, it started at 23, went to 34, so I got a difference of 11.7. Final minus initial, that's going to be a positive change in temperature. Now remember, I'm going to calculate Q down here before I do anything else over here, but let's at least throw in the measurements. The mass, 93.19. And let's see, the change in temperature. Well, I see that it started at 225. That's the initial temperature. But we're going to do final minus initial. Which one of these two do we use for the final temperature of the metal? Well, the metal is in here at the end, so it reached the same final temperature that water did. So we're going to do, hopefully I got that right, 34.7 is final minus 225, which was initial. I got negative 190, which makes sense. It should be going down in temperature. That's why it's negative. The water's going up. It's positive. All right, now remember, we do the calculations on this side first. So Q equals MC delta T. For my Q, I got 2190 joules. And of course, if that's how many joules I got here, it will be the same over there, but what's the only difference that there'll be? That's right, the sign will be the opposite. So I'm using negative 2190, I'm using my mass, and I'm using my change in temperature. I solve for C, and I get 0.124. Did you guys look it up on the internet? How did we do? Because I think it was copper. Ooh, not so good. Maybe the stirring didn't help at all, but it might be a good... Oh, wait, whoa, whoa, whoa. Do you guys see that negative sign? What's that negative sign doing in there? I have negative divided by negative. You know these are always positive. What? Oh. Anyway, get rid of that negative sign. I don't know if I can scribble it out. Let me scribble it out. That's really bothersome. There we go. So here's my question. If we didn't use a styrofoam beaker and some of the heat escaped, could that have accounted for our specific heat being too low? So what I want you to do is I want you to try writing up an error analysis question. Which of our measurements would have been affected by heat escaping, and how would it have impacted our calculations? Well, the measurements that would have been impacted is, I think if it had escaped, our change in temperature would have been lower, right? It would have been too low. In other words, if the heat had stayed in, the water temperature change in temperature would have been higher because we would have gotten higher there. So we're dealing with a change in temperature that's too low. If it's too low there, our heat absorbed will appear to be too low. And if our heat absorbed is too low, it'll be too low there. And when we divide by that and divide by that, we will get a heat capacity that is directly related to the too low Q value, and we are going to get a value that's too low. I think that does explain why our heat capacity was too low. So there you go. All right. Very nice. So you might wonder, is there another way to do this? Of course there is. If you can see what we're doing here, which is we're saying that the heat absorbed by this one has got to be the same as the heat absorbed by that one. But of course, remember, this Q is equal to negative that Q. So if you decide to set these two equal to each other like that, remember that you got to have a negative sign in there somewhere, because Q does not equal Q. Q equals negative Q. But this is a great way to set it up as well. But if you're going to do that, make sure that you label the little waters and the little coppers or whatever your metal is, so that you can distinguish between the heat capacity of one and the other and the change in temperature of one and the other. But it should work fine just as well.